Welcome back, Focus Learners. Today's explainer is all about taking some pretty complex ideas and making them, well, crystal clear. We're going to take a trip from the macro world, the stuff we can actually see and touch, straight down into the microscopic 3D geometry of solid-state chemistry. We're going to take the invisible, structural math of crystals and make it highly visual, super intuitive, and honestly, pretty fascinating.
So, look around you. You are completely surrounded by solids. But what exactly makes up a solid crystal? And why is there actually empty space hiding inside it? Imagine taking a really beautiful emerald ring, crushing that gemstone down into an ultra-fine powder, and then zooming way in with a powerful microscope. You wouldn't just see a random mess of dust. You'd see a highly organized, repeating structural lattice. It kind of challenges everything we think we know about what a solid really is. Because as we'll see, solids are really just a masterclass in packing tiny spheres into tiny spaces.
To understand how it all works, we have to start with our fundamental building block, the unit cell. Think about it like this. If a massive crystal lattice is like an enormous brick wall, the unit cell is that single, perfectly shaped brick. It's the absolute smallest repeating 3D geometric structural pattern inside a space lattice. By understanding just one of these tiny unit cells, we literally decode the visual math for the entire crystal.
Okay, let's dive into this. Here's our mental roadmap. We'll start with the building blocks, then decode simple cubic, body-centered cubic, and face-centered cubic structures, and wrap the whole thing up with voids and essential formulas.
Section 1. The crystal building blocks.
So, nature is constantly playing this microscopic game of Tetris, right? It's trying to pack geometric spheres into a 3D box as efficiently as possible. But because you just can't pack perfectly round spheres flush against each other, there will always be gaps. Always. We measure this battle using packing efficiency, which is the volume occupied by the atoms divided by the total volume of the cube, times 100. And on the flip side, we have the empty void space left behind.
Section 2. Simple cubic.
The simple cubic is the first and most basic of our three structures. Let's map out the math visually. In a simple cubic structure, atoms are sitting only at the 8 corners of the cube. But here is the trick, and it's super important. Those corner atoms aren't entirely inside our single unit cell. They're actually being shared with the neighboring cells stacked all around it. Because it's on a corner, only 1/8 of that spherical atom sits inside our specific cube. So if we do the logical step-by-step math here, 8 corners multiplied by a 1/8 contribution equals exactly 1 complete atom per unit cell.
6. This is an essential structural stat known as the coordination number. In our simple cubic lattice, if you look at any single atom, it is touching exactly 6 adjacent neighbors. So that's its coordination number, 6. Now for the edge length relation, which is nice and straightforward. A equals 2r. Here, A represents the edge length of our cubic cell, and r is the radius of the atom. Since the corner atoms touch each other directly along the edge of this specific cube, the length of the edge is literally just the radius of one atom plus the radius of the next. Boom! A equals 2r.
And the numbers brilliantly illustrate exactly how porous this basic structure is. Because the atoms are just sitting at the corners, the simple cubic space only achieves a 52.4% packing efficiency. Think about that for a second. That means a massive 47.6